Hey, welcome back. And right after I hit stop, I saw a problem. I just can't add. I subtracted 5 instead of adding 5 inside this last example. It was in that previous video. So 9 minus 2, 7, and then 7 plus 5, 12. Sorry about that. So it's easy to fix, put a 12. Oh, so easy, just put a 1 in front of the 2. That's what you get for not being careful. I'm not a very careful person. Okay, the next, so in addition to adding, subtracting, and multiplication matrices by scalar, and the transpose operation, which is brand new, we get to the operation of multiplication. To multiply two matrices together is a fairly involved operation. It involves a whole bunch of dot products. You essentially have to take the dot product of each row of the first matrix with each column of the second matrix and do it in a particular ordered way. So knowing that dot products are quite involved, and knowing that if you have a lot of columns and a lot of rows in your matrices, you're going to have a lot of these dot products to do, you can imagine how much work it is to multiply, let's say, a 5 by 5 matrix by another 5 by 5 matrix. You have a ton of dot products that will be involved in that operation. When we will do that, I'll show you exactly how to do the matrix multiplications, exactly how they're defined, both algebraically and visually, graphically. But before we learn actually the process of multiplication, I want to show you some of the properties of that multiplication and some of the restrictions on multiplication that will come about because of those definitions. First property, or first thing to watch, is that we're not allowed to multiply any two matrices together. They have to have a certain size. So we have yet another distinction with numbers. Like if I give you two numbers and tell you to multiply them, you're like, you know what, I can't multiply that one. It's not, something's wrong with that 7. I can't multiply that by 5. Like that never happens. If I give you two numbers, you can always multiply them. But if I give you two matrices, A and B, and say, multiply them, you can turn back and you can say, I can't multiply them. It's impossible, given the definition that I'm about to show you. I'm about to show you what that definition is. So without showing the definition, you just have to trust me that if you take let's say a matrix that's m by n and another matrix that's n by p, you are allowed to multiply them in that order as long as the number of columns of the first matrix in that matrix multiplication is equal to the number of rows in the second matrix in that multiplication. So the number of columns of the first matrix must be equal to the number of rows of the second. And the precise numbers otherwise don't matter, and the precise sizes don't matter. So the number of rows of the first matrix can be anything, and the number of columns of the second matrix can be anything. One consequence of this is that this automatically tells us that order of multiplication matters, which is another distinction with numbers. 5 times 7. You calculate it out, and then I ask you for 7 times 5, you're like, that's the same thing. Why would you ask that? That's true for numbers, but not true for matrices. It is not always going to be the case that A times B is equal to B times A, and it's actually only going to happen sometimes in very, very special circumstances when these two matrices A and B have a special relationship with each other. Next item for matrix multiplication, before telling you what this operation even is I can tell you what the resulting size is going to be of the new matrix that is created. So you multiply two matrices together. Yes, a new matrix comes out. I know I said dot product, and dot product creates numbers, but those numbers from the dot product are going to fill entries in a new matrix. What if I give you a 3 by 5 matrix and a 5 by 7 matrix, or 5 by 9 matrix, and ask you to multiply them in that order? So the 3 by 5 multiplied by the 5 by 9. What comes out of that operation will be a 3 by 9 matrix. So you can think about that the following way. Put the matrices side by side with their sizes, not with their numbers, but their sizes. So the 3 by 5 next to the 5 by 9. Those 5s in the middle are the same. That means that the multiplication is permitted it's allowed, then the 5s will kind of, I don't want to say cancel, but for this picture, they cancel. So the inner dimensions of the matrix multiplication cancel out, and the new matrix will have the outer dimensions. So the number of rows in the first matrix and the number of columns in the second matrix. It's kind of like a baby that looks a little bit like both parents. And these are matrices, so that sounds horrible, but I don't know what else to say. Now, if you try to go the other order, if you try to do 5 by 9 multiplied by 3 by 5, it doesn't work. That's an undefined operation. The second example here, it's again not showing the matrix, just telling what the sizes of the matrix are. You have a matrix A that's 1 by 4, so we're at this one now. We have a 1 by 4 and a 4 by 4. We can multiply them in that order. What will happen when we put them side by side, 1 by 4 times 4 by 4, is the inner dimensions will cancel and we'll create a 1 by 4 matrix. But we can't go the other way around. We cannot multiply a 4 by 4 and a 1 by 4 in that order. We can do A times B, but we can't do B times A. The inner dimensions will not cancel when we stack them up. The last one on the slide is if we have a 2 by 3 and a 5 by 2. So we put them side by side, put their sizes side by side, 2, 3, multiplied by a 5, 2. This is not cross product, okay? We're not crossing those two element vectors. It's just a shorthand notation to describe the size of two matrices. First matrix, 2 rows, 3 columns. Second matrix, 5 rows, 2 columns. Notice that the inner dimensions do not cancel. We have a 3, we have a 5. That tells us that this matrix multiplication is not defined. But look what happens if we flip the order. What if I take this 5 by 2 and put it here? So what if I do B times A instead? Well, this one is allowed because the inner dimensions match. They'll cancel out and the resulting matrix will be 5 by 3. 5 rows, 3 columns. And this is kind of like telling you the end of a story. So here's the beginning, here's the very end. Now you're all wondering what's the middle. So this is what's going to happen when you try to multiply matrices, but how do you actually do the multiplication? So I want to give you a preview for that. I want to just show you what matrix multiplication looks like using a fairly simple example, a 2 by 2 matrix multiplied by another 2 by 2 matrix. I recommend pausing the video and getting some more colors. So if you're writing everything in pencil, get more colors, as many as you can find. Okay, you've all come back and you got like, do I have, see, I'm delinquent. I usually have like this wonderful stack of pens and pencils, different colors, but guess what I got? Sharpies. And there's nothing I can write on the wall with Sharpies, but there's nothing I can really do with Sharpies. So you should have a bunch of colors that look like this right now, but pens. To make beautiful notes, to kind of copy what I'm doing with this like electronic pen. And the reason I don't have any pens of colors is because my kids take all my pens. Like I'm down to this as a one mechanical pencil that they haven't stolen from me yet. All right, so I'm going to show you what the matrix multiplication looks like. A times B. I'm going to put them side by side. 1, 2, 3, 4. That's the matrix A, and beside it I'm going to put the matrix B. 5, 6, 7, 8. So remember, if we have a 2 by 2, well, I'm going to be consistent with my notation. 2 comma, and there's no commas, is there? I'm just going to copy what I have. Yeah, there's commas. 2 comma 2 multiplied by a 2 comma 2. The inner dimensions cancel. I'm going to get a 2 by 2. So I'm going to make a space for that. To put those numbers. But actually, I'm going to leave more space to actually show the multiplications. Now, get another color. and do the following. Circle the first row of the first matrix and circle the first column of the second matrix. The number of entries in that first row must be the same as the number of entries in that first column of the second matrix. This is what I'm about to do is why that size requirement is there, that these two entries, or these two dimensions, the number of columns of the second matrix must be equal to the number of rows of the first matrix. That requirement forces this to happen. It forces what I'm about to do to be possible. I'm going to take the dot product of the first row with the first column, and I'm going to put it in the top left entry. So 1, 2, dot product, 5, 7. And then above this, I'm going to write down that this new matrix, which I'll call C, let C equal A times B. C11, C11, not C12. C11 is going to be first row, all columns, A1J, dot product, B, I1. So I meaning all the elements. Let me make sure I got this right. I may have just screwed it up. Aij, first row, all columns, and BI1, all the rows in the first column. Yes, okay. So Aij is the first row of A, and BI1 is the first column of B. So that's my top left entry. Okay, and we're going to do the other ones, but I just want to put a number down for this. So we have 1 times 5 plus 2 times 7, 14. And then I'll fill it in, 19. So the first element is 19. Now the second element, get another color. I'm going to take that first row, circle it, and now I'm going to take the dot product of that with the second column in that second matrix B. And I'm going to put that at the top right. 1, 2, dot 6, 8. That's C12, first row, second column, and it's going to be the dot product of the first row, A1J, dot BI2. Row 1 of A, dot column 2 of B. So let's do that dot product. 1 times 6, 6. 2 times 8, 16. So that'll be 22. And now get another color. I'm going to do for second row of that first matrix times the first column. And that'll go down the bottom left. 3, 4, dot 5, 7. So let's do the dot product. 3 times 5, 15. 4 times 7, 28. And then add them together, 43. And then the last, I should put that up above. This is C21. and it's A2J dot product BI1 row 2 of A dot column 1 of B, and then take one more color. I still have blue, I'll use blue. 34.68. Last row dot last column is going to go in the bottom right entry. 34.68. So 18 plus 32, which is 50. And that's our answer. You don't need to show all these steps for it, and you don't need to use all these colors, but at least in one note, somewhere handwritten, do it with lots of colors. I promise you it'll help you remember what to do. Oh, and I forgot to write down the last entry in terms of the I and J stuff. C22 is equal to A2J dot BI2. So row 2 of A dot column 2 of B. I put a little comment at the bottom. If A and B were, let's say, 7 by 7, then the, let's say, 5,6 entry of A times B would be row 5 of A dot product column 6 of B. So that's how you would get the 5/6 entry of a 7 by 7 times 7 by 7 matrix multiplication. You'd have a dot product between row 5 of the first matrix in that multiplication times, or dotted with the column number 6 of the second entry inside that multiplication. We'll break here and go to another video.